The second talk is live. The presenter is Shi-Xiong Chi. He's a PhD student working with K.K. Ramakrishnan at University of California, Riverside. And Shi-Xiong's research interests are 5G, NFV, and serverless computing. And this is the topic of the presentation today.
So thank you. Thank you for the introduction. And so today I'm going to introduce our recent work on serverless computing. So we have been focusing on making serverless computing more resource efficient and high performance. And a number of us in UC Riverside has been involved in this work, including Leslie Moniz, Zidong Zhen, Yanqing Wang, and my advisor, K.K. Ramakrishnan. So serverless computing has growing popularity because it makes it easier for the user to deploy and develop cloud applications. The user only needs to focus on the application code without worrying anything about the application management. And the serverless computing also removes the need for traditional always-on server components. And this can reduce users' operational cost and complexity and greatly improve service scalability and availability. But the issue is the serverless computing doesn't focus on performance and efficiency as much as flexibility, and fails to provide low latency processing and low resource consumption. Our solution, SPRIGHT, is designed to address this issue. So by leverage shared memory and event-driven processing, SPRIGHT achieves high-performance, resource-efficient serverless function chain. So let's first take a look at the key components in a service cloud. So we mainly started Knative, which is a representative of many of these open source platforms. So in a Knative control plane, it has this placement engine, autoscaler, metric server, which are all used for facilitate resource orchestration. And in the data plane, we have this ingress gateway, which is used as an entry point of the entire service cloud, performing tasks such as TLS termination, authentication. And we have this message broker, or sometimes we call it front-end proxy, to support function chaining. This is very critical because with function chaining support, user can take advantage of microservice paradigm and build complex cloud applications as a composition of individual service functions. And the last key component I'd like to mention is this function part. So it is used for function execution, and it has two parts. The first is the user container, which is the one that really used for application execution. And the second is the sidecar proxy. It provides several important functionalities like metrics collection, queuing, health checks, which are all used for control plane's responsibility. But this data plane design comes with lots of complexity and overheads, so I will perform overhead auditing of a typical serverless function chain setup in Knative to explain how the overhead is introduced and by following the data paths of a request. So in the first step, there is an external client. It sends a request to this function chain in the service cloud. But this request is first intercepted by the ingress gateway. And this process introduces one copy, one context switch, 3 interrupts, 1 protocol processing, 1 deserialization. And in the second step, the request is routed from the ingress gateway to the front end for coordinating invocations within the function chain. And this process introduces 2 copies, 2 context switches, 4 interrupts, 2 protocol processing, 1 serialization, and 1 deserialization. And in the third step, which happened within the function chain, so the request is routed from the front end to the first function in the chain. And as you can see, this processing introduces even more overhead, as you can see in the column 3. And especially the existence of this sidecar, which in handling the request to the function part, also introduces amount of overhead. And plus, because this sidecar is constantly running, so it has a CPU resources allocated to it. And in the next step, after function 1's processing is complete, you end up having to go back to the front end and go through all of this overhead again. And in the last step, a new request is registered at the front end and sent to the next function in the chain. And what you can see is the overhead keeps adding up. So based on this overhead auditing, what we can find is we have 4 takeaways. So the first takeaway is there's excessive extra overheads in terms of copies, context switches, interrupts. And we have excessive duplicate protocol processing just for communication within the function chain itself, and because of the need of intermediate routing component like front end. And there is lots of unnecessary other overheads for deserialization and serialization, and you have this individual constant running component like sidecar. So the existing service framework seems to be consuming way too much overhead. And we've looked at a number of open source platforms, and here we just use the Knative as a typical one to explain all of the overhead here. But we believe this is true for many of the other open source commercial platforms, and although we don't know that for sure. So we have improved serverless computing by leveraging eBPF-based event-driven capability plus shared memory processing. And because of those, we are able to reduce the data movement overhead and make the processing to be strictly load proportional. So it really looks like a true serverless one. And we have 3 optimizations in Sprite. So for this first optimization, because there's lots of overhead introduced by this sidecar, so we are going to use event-driven proxy to replace it. And for the interfunction data movement, we use shared memory processing so we can avoid lots of overhead, like data copies, context switches. And we introduce this Sprite gateway component to consolidate protocol processing. And we are also going to use this direct function routing, or DFR, to go from one function to the other one directly. And this can help us eliminate the need of an intermediate routing component like front end and simplify the interfunction invocations. So now I will give more explanation on each optimization. And for the first optimization, we are going to take advantage of event-driven proxy. We call these proxies eProxy and xProxy because we are using eBPF-based sidecar. And on this Sprite gateway part, as you can see, we have this eProxy. We use it for monitoring IP tables acceleration. And on Sprite gateway, as well as the user function, we have this sProxy. We use it for monitoring security routing. So both of them are doing event-driven processing, either at the virtual Ethernet or at the socket level. And there are several benefits of using event-driven proxy. So first, as its name suggests, it's purely event-driven, which means it consumes no CPU overhead when there are no requests. And because all of these event-driven proxies, they run in the kernel, so we can avoid extra user kernel boundary crossings and save lots of overhead. And second, so to optimize the data exchange between the functions, we use shared memory processing. And to handle protocol processing, we use this Sprite gateway. So it is an entry point of a function chain similar to the front-end proxy in a Knative environment. And we use Sprite gateway. So Sprite gateway uses kernel processing to get the layer 7 payload and move the payload into shared memory for further processing within the function chain. And because shared memory processing depends on or relies on the packet descriptor, which is actually a pointer to data in the shared memory, so we fully exploit our event-driven proxy in supporting shared memory processing. So we use this eBPF socket message, which resides in our sProxy, to deliver packet descriptor between functions. And the routing is supported by eBPF socket map. And because of this event-driven based processing, so we are strictly load proportional compared to a polling-based approach like DPDKRT ring, which constantly consumes CPU resources. And because having the broker and front end perform invocations between functions is unnecessary, that introduces lots of additional overhead. So we use this direct function routing to go from one function to the other one directly by using the routing rules in the eBPF socket map. And this can help us reduce the end-to-end latency of function chain processing and improve the service scalability. So let's look at the overhead auditing of Knative and Sprite. So the left one is the Knative table, and the right one is the Sprite table. And what you can see is that there's dramatic overhead reduction in every single dimension. And this shows that Sprite's event-driven shared memory processing brings substantial overhead reduction for communication within the function chain. So let's take a look at the quantitative analysis through several realistic workloads. So we use this Online Boutique workload, which was brought in by Google, and I believe many of us use it. So it's intense web traffic with 10 different functions, and there are 6 different sequences of function chains in this workload, and I'm going to talk about this one in detail. And we also have 2 other workloads for motion detection, like IoT behavior, and a more heavyweight one, like this parking image detection and charging. So we also looked at. So here's the evaluation with the Online Boutique workload. So we compare our approach with a baseline Knative setup. And we also compare with serverful microservice-based approach using gRPC for inter-function communication with no sidecar. And to understand the benefit of our event-driven shared memory processing, we additionally compare with a DBDK variant of our design, which we call it as D-SPRIGHT, to differentiate with our event-driven design, which we call S-SPRIGHT in the evaluation. And for these different alternatives, we configure the load levels to make sure they operate close to their maximum capacity. And here's the results. What you can see is that both D-SPRIGHT and S-SPRIGHT maintain a stable RPS of, and which are like almost 6 times higher than Knative. And when you look into the latency results, the Knative shows clear overload behavior with very high time latency. But when you look at the gRPC, of course, it's certainly better, but its throughput and latency is still much worse than our design. And this is because SPRIGHT's shared memory processing reduces communication overhead within function chain. And so we can achieve a better performance even with a much higher traffic load. And here's the result of resource efficiency. So the Knative setup consumes 26 CPU cores, and the gRPC setup consumes 36 CPU cores. But on the other hand, the D-SPRIGHT consumes 11 CPU cores because DBDK uses polling and keeps consuming CPU resources. But S-SPRIGHT consumes only 3 CPU cores. And this shows that SPRIGHT's event-driven mechanism makes its shared memory processing more resource efficient. So I do not have time to walk through the result of the motion detection and the parking one, but here's the main takeaways we got out of those experiments. So for the motion detection, the takeaway is SPRIGHT's event-driven design sidestepped the need for cold start by keeping function warm at a minimum cost. And for this parking one, the takeaway is SPRIGHT's event-driven feature makes it more resource efficient, even when we keep functions warm, compared to pre-warmed Knative functions. So given that we are using shared memory for data sharing, so there's always a concern about security and isolation between service functions. So in SPRIGHT, our trust model assumes that functions within a chain trust each other, but functions in different chains, they may not. And we provide 2 features to construct a security domain for each function chain in SPRIGHT. So for the first feature, so we assign a private shared memory pool for each chain in SPRIGHT by leveraging DBDK's multi-process support and assign different shared data file prefix to different function chains. And in this way, we can separate the memory pools of different chains. And for the second feature, if you remember, we use S-proxy when communicating within or between functions within the same function chain. So we leverage this feature and use S-proxy to perform inter-function packet descriptor filtering. And this way, we can avoid unauthorized access to the shared memory. So to conclude, SPRIGHT is an event-driven shared memory framework that we bring the power of serverless computing to the forefront by improving data plan performance, reducing overhead, and bringing the process to be strictly load proportional. So for intense web traffic, SPRIGHT achieves much higher throughput, much lower latency, and at the same time, consumes 30 times less CPU usage. And for the IoT workload, SPRIGHT is obviously better than Knative, even with pre-warmed functions, and because it can support multiple warm functions at a minimum cost, so it can sidestep the cold start issue. And we already open sourced the SPRIGHT code at GitHub, so if you're interested, please take a look at it. And thank you very much.
A question over there.
Yeah, thank you for a great talk. I have a question on, for the benefit of scaling functions individually, it's not always true that all the functions of a service train co-locates on the same workload, or on the same work node, or there are chances that are being routed to a different work node, how it might be benefit from this kind of a shared memory scheme. And the second question to the continuity of the first one is that more often than not, we use those kind of in-memory caches or messaging middleware to chain up the different pieces of a function chain. So what's your thoughts on kind of the possibility of co-designing your mechanism with this kind of a messaging or caching middleware? Thanks.
So for the first question, you mean like if we want to use this shared memory, right? We need to consolidate all these functions in the same chain on the same node. So this is true. But in our paper, what we discussed is like if we want to do scaling, right? Or if you want to do placement, you need to take these function chains as a unit to scale them, to place them. But of course, there may be some like drawbacks of this approach. You may need to see more fragment. But there might be some optimizations we need to do in the future, like to minimize the fragment by deploy the function chain as a unit on different nodes.
Yeah, and there is also the routing thing.
Yeah, the load balancing is another issue like we need to address.
More questions? So let me ask a question. So I think you proposed a number of effective optimizations that improve this overall significant improvement in performance over Knative. So the question is, why the kind of the original serverless platforms were so ineffective? They just didn't care. They just put something together quickly to be first out there, or maybe there was some kind of deeper reasons. I don't know. Sometimes people do things for modularity or whatever reasons. So what's your take on this? Why are you so successful in what you did?
So like you mean, so can you repeat your questions? Like,
yeah, so
get the idea.
The reasons why you were so successful, right? You propose a number of techniques and you show the performance became much better. Why they didn't do it in the first place, in the Knative or other existing platforms?
So the things, so what we think is like Knative, this kind of serverless platforms, right? They more focus on the flexibility and scalability, but they usually ignore like the performance and efficiency. Like using this sidecar model is not very efficient and it consumes lots of overhead and lower down the data plan performance. So that's why we like want to use this event-driven shared memory processing to like kind of optimize the data plan performance on top of the Knative and to balance several like factors like performance, efficiency, flexibility, scalability. That is what we want to do.
Okay. Can we give the mic to KK so that I think KK is eager to say something? No, have the mic.
Just a philosophical answer. You know, a lot of capabilities get started by providing functionality that people need. And serverless answers a need, which is I want to give the capability for somebody to use a cloud environment by just focusing on what they want to develop. So first, to offer something is great because it gets people to get started to use it. But afterwards, follow-on people like us come in to look to improve performance because that's how you end up actually furthering the state of the art.
Okay, thank you, KK.
Yeah, thank you, Sergey.
So let's thank Shishong again.